Now let us consider the second order system. Now we use the concepts of the poles and zeros and the transient response to the second order system. Compared to the simplicity of the first order system, which was quite simple, a second order system exhibits a wide range of responses that must be analyzed and described, whereas varying a first order system parameters changes the speed of the response. That is, only the speed of the response is changed in case of this first order system, and the changes in the parameters of the second order system change the form of the response. However, when we change the parameters of the second order system, then the form of the response will change. So a second order system can display characteristics much like the first order system. Depending upon the component values, it display damped pair oscillations are the transient for its transient response. Now we can discuss the each response and show how we can use the poles to determine the nature of the response without going through the procedure of partial fraction expansion followed by the inverse Laplace transform. That is what we have done in the first order case. We can use it for the second order case, and by seeing at the equation how we can reach the conclusion and how we can drive the equation. Now let us take the case of this case. This is the transfer function, and this transfer function is actually derived from this transfer function, that is b, that is s square plus as plus b. So this transfer function has no zeros and two finite poles, and by assigning the appropriate values to this a and b, by assigning the appropriate values to these parameters, we can show all the possible second order transient responses. So for the sake of the understanding, while varying this a and b, we can show the different responses. What are the different responses that can be obtained in this case? Now first we come with the overdamped, that is step response. Now let us consider the transfer function. Let the transfer function can be represented by c. This transfer function can be represented by cs is equals to 9 divided by s into s square plus 9s plus 9, and which can be written as 9 divided by s into s plus 7.858 into s plus 1.146. So these are the two roots that can be obtained. So this is actually the step response of the system. This is the transfer function, and this is the step response, that is cs. So in this case it is we have the these two terms and one s. As we already know from the previous case that input pole at the origin, that is s is basically the input pole which is at the origin, generates a constant force response. Each of the two system poles, that is s plus 7.8 and s plus 1.146, that is two system poles on the real axis, generates the exponential response. As we have already discussed, it generates an exponential natural response whose exponential frequency, that is e raised to power, is equal to the pole location, that is location of the pole. Hence the output, initially we can write the output, that is output can be written as initially Ct equals to k1 plus k2 e raised to power first pole, that is for what is the first pole, minus 7.854t plus k3 into exponential of minus 1.146t. Okay, so this and the response would be like that. So this kind of the response is known as the overdamped response. So without going to the tedious calculations, we can easily get the response that from seeing that transfer function and the response of the system to step input, we can easily see that if we have the poles, real poles on the negative axis, then we can say that it gives the overdamped step response. Now for an overdamped response, if we have the two real poles which is given by sigma minus sigma 1 and minus sigma 2, then for a natural response, the two exponentials with time constant equal to the reciprocal of the pole location, and the response is in this case is given by k1 e minus sigma 1 t plus k2 into e minus sigma 2 t. So if we have the two real poles, then the response would be like that. Now let us take the case of the underdamped case. Let us suppose that in the underdamped case, let us suppose the response of the system would be 9 s square plus 2s plus 9. For a step input, response of this transfer function for a step input is given by this. Now this has two poles. One is two poles, and the location of poles is minus 1 plus minus j root 8. So in this case we have the two poles, and in that we have one real pole and one, that is we have one real part of the pole and one imaginary part of the pole, that is it is located here, this. Okay, one real part and one imaginary part. Now if we plot that response, we will see that for that case the response would be somewhat like that. That is, it has one exponential decay generated by the real part, that is exponential decay generated by the real part, and second is sinusoidal oscillation generated by the imaginary part of the complex pole. That is, this one is generated by the real part of the complex pole, and this oscillation, sinusoidal oscillation, is generated by the imaginary part, that is this one, of the complex pole pair. As we have already seen that the time constant of the exponential decay, this one, time constant of this exponential decay is equal to the reciprocal of the real part of the system pole. It is the reciprocal of the real part of the system pole. That is, we can say that the time constant of exponential decay is the reciprocal of the real part of the system pole, and the value of the imaginary part is the actual frequency of the sinusoid, and this sinusoidal frequency is given the name the damped frequency of oscillation, and it is denoted by omega d. Finally, the steady state response was generated by the input pole, which is located at the origin, and we call the type of response as the underdamped response. That is one which approaches the steady state value via the transient response, that is damped oscillations. That is, oscillations are damping. Now this word underdamped. Now overdamped refers to the large amount of energy absorption in the system which inhibits the transient response from overshooting and oscillating about the steady state value for a step input, and as the energy absorption is reduced, an overdamped response will become the underdamped and it exhibits the overshoot. Now let us take a small example. From this it is clear that how we can get the conclusion of that overdamped response. Let us consider a system and the step input is provided to it. Now we see, after solving this s square plus 10s plus 200, we get the response as minus 5 plus minus j 13.23, and the real part minus 5 is the exponential frequency of damping. That is, real part we have s is equals to minus 5 plus minus j 13.23. So the real part of it, that is 5, is the exponential frequency of damping, that it comes with that exponential frequency minus 5t. Okay, and the imaginary part, that is 13.23, is the radian frequency for the sinusoidal oscillation. So it is the radian frequency, that is omega d, for the sinusoidal oscillation. So finally what the response we are getting in this case is Ct is equals to K1. K1 is due to this step response, then we have E minus 5t, this one, and then K2 cos of 13.2t plus K3 sin of 13.2t, and then we solve it, we get K1 plus this K4, let us, these are constants, E minus 5t cos of 13.23t minus phi, and phi is given by tan inverse K3 by K2, and K4 is actually the magnitude of this K2 plus K2 square, under root of K2 square plus K3 square. Now from this we conclude that if suppose that we have the complex poles which are given by minus sigma d plus minus j omega d, having real part and imaginary part, then the natural response can be written as Ct is given by a e minus this one sigma dt into cos of omega dt plus phi. Omega t is basically this one. So damped sinusoid with an exponential envelope whose time constant
is equal to the reciprocal of the pole's real part, and the radiant frequency of the sinusoid, that is damped frequency of oscillation, is equal to the imaginary part of the pole. So if it is of that type, then we can get the answer would be of that type, and response would be this one, that is underdamped. Now let us consider third case, that is undamped case. Now let us consider a transfer function which is let us consider a response 9 s into s square plus 9. Now we will see that it has two imaginary poles, that is s is equals to plus minus j3, which can be plotted on this imaginary axis. Now it has one pole which comes from the at the origin, that comes from the unit step input, and two imaginary poles. Okay, the input pole at the origin generates a constant forced response, and the two system poles, that is imaginary poles, on the imaginary axis generate a sinusoidal natural response whose frequency is equal to the location of the imaginary poles, that is 3. Okay, so the response in this case would be equal to like that 1 minus cos of 3t, that is the output can be estimated in this case as Ct is equals to k1 plus k4 cos of 3t minus 5. Okay, and the response would be like that. So it is known as the undamped response, that is there is no exponential term, so there is no decay. So the absence of the real part which creates the exponential poles, so we can't have the decay of this response. It means that it will move like that without decay. Now it can be summarized as that if we have the two poles at the imaginary axis, then in that very case the natural response undamped is the undamped sinusoid with the radiant frequency equal to the imaginary part of the pole, and this is written as a cos of omega 1 t minus 5 if we have only two poles, that are imaginary. Okay, now let us consider the next case, that is critically damped. Let us consider the system response is given by 9s s square plus 6s plus 9, that is 9 divided by s square plus 6s plus 9, and finally we are getting 9 divided by s into s plus 3 square. So it has one pole at the origin, okay, from the unit step input, and two multiple real poles that come from the system. Two multiple real poles are there that come from the system. In this case it is minus 3. The input pole at the origin generates the constant forced response, and the two poles at the real axis, that is minus 3, generate a natural response consisting of exponential and an exponential multiplied by the time, where the exponential frequency is equal to the location of the real poles. Hence, in this case, the response would be like that: Ct is equals to k1 plus k2 e minus 3t plus t k3 into t e minus 3t. Okay, so this type of response is known as the critically damped response. It is called the critically damped response. These are the fastest possible without the overshoot. That is the characteristic of the underdamped response also. These are very fast without the overshoot. Now these observations can be summarized by this one, that is, if we have the overdamped, if we have these two poles on the two real axes, then we get the overdamped response. Then if we get the two complex poles, then we get the underdamped response. And if we get the two imaginary poles, then the solution would be like that, and we get the undamped response. And critically damped, which is the fastest, and if we have the two real poles, then we get the critically damped response. Now these responses, all responses of the four cases are superimposed, and also in this case we see that this is undamped, oscillations are there and it will not damp out. Then we have the underdamped, then it is overdamped, and also it is critically damped. This is the best. So critically damped case is the division between the overdamped case and underdamped case, and is the fastest response without overshoot. So we want the system to be critically damped, but it depends upon the situation. Now some of the transfer functions are given, which you have to do at your own end. So four transfer functions are given. So from this you can find out the responses, as the answers are also given in this case. As you can see in the first case, we will have the two complex poles, and its answer would be like that. Now let us take the second case. In the second case, we will have the two real poles, so its response would be written like that, and it is the underdamped case. First one was the overdamped case, and the first one was the underdamped case, which has two real poles, and second one has two complex poles. Then in this one has two complex poles. So third one has the two real poles, that is the fourth case. So it is a critically damped case, and solution would be like that. And last one is actually it had two imaginary poles, so it is the undamped case, and it can be written like that. So this is how you can do. You can take the root of this denominator and find out that what's the root, and then use the equations, use this what we have discussed here, so that we can get to the conclusion, or we can get the response of the system without having that task of finding the Laplace transform and then the inverse Laplace transform. So it is one of the easiest way to do that. We have system transfer function of the system, and we can easily get the response of that transfer function. We can easily get the response of the system without going into detail of that. So it is for the second order
system. I hope you understand the topic well, and you can do the problems at your own end. Thank you.